Hello and welcome to everyone. So today we have the second lecture of the week 11th on the course on financial econometrics. So in continuation of the last classes, today also we will discuss about the volatility models. So till now what we have discussed about the univariate models. Today we will discuss about the multivariate form of those volatility models. So specifically we will be discussing about multivariate GARCH models. So what we have discussed till now, the univariate form. So one of the limitations of univariate model is that the conditional variance of each series is forecasted or fitted assuming that it does not depend on any other variables. This has the limitation based on the two concerns. One, if there is the volatility spillover between the markets or assets, in such situation, then univariate models will be misspecified. What is volatility spillover? Volatility spillover is that if there is the volatility either increasing or decreasing in one sector, it may affect the other sector. Or if there is any volatility change in one market, it could have effect on the another market. So what we call the contagion effect. And it is obvious we can observe in the financial world that if something happens in one market, that uncertainty then volatility spills over to the another market. For example, if something happens in the US market, then it do have impact on the other financial markets. For example, we have seen the global financial crisis, where the crisis started with the US market, it has affected across the world. Similarly, we could see, for example, if something happens in the oil sector, oil prices, if there is the volatility in the, let us say, in the commodity market, it could have effect on the equity market. So these are the basically phenomena of the spillovers. So if there is the spillover, that means the one particular asset's volatility do depends on the volatility of other assets or other markets. However, while we are doing univariate modeling approach, in that case we are assuming that every asset's volatility is independent of others. The second point is that there is a lot of different situations we face where we are concerned with the covariance matrix also, not only with the variances. For example, finding the hedge ratio or the portfolio value at the at risk estimates, or when we are talking about the capital asset pricing model beta, and there are many other occasions where we are concerned with the covariance structure also, not only with the variance structure. So in such situation, we have to think about the covariance modeling in addition to the variance modeling. So that's basically when we talk about the multivariate GARCH modeling. That means we are talking now that we will try to model both variance as well as the covariance structure. So this multivariate GARCH is basically nothing but the extension of the univariate GARCH models to model the time varying variance and covariance matrix of the multiple time series. And this is quite useful. For example, in the portfolio optimization, where we are concerned with the number of assets, or risk management, again where we are concerned with not a single asset rather than more than one assets, or the volatility spillover across the assets, or measuring the contagion effect. So in all situations, this multivariate GARCH comes in handy. So this model the conditional variance and covariance matrix, which is basically which we represent using HT, so a vector of time series YT, let us say up to n. So that's basically the multivariate GARCH model we do here. So the basic formulation is similar as we have discussed into the GARCH model. Only the difference is there. Here we are assuming that both variance and covariance matrix is assumed to be time varying here. There are the three main classes of multivariate GARCH modeling we have. One, the VECH, second, the diagonal VECH, and BEKK. So all three we'll discuss today. So let's first formulate a general form of the multivariate GARCH model. So let's assume yt is a vector. We'll be using the matrix notation. So let us assume yt is a vector of n time series. So those series could be returns. So that is y12, y22 and ynt. So here the model can be expressed as yt plus mu t plus epsilon t. So here this yt is the nothing but the here vector of n series. This mu t is the conditional mean vectors and epsilon t is the vector of residuals. And here this ht is the conditional variance and covariance matrix of this error term. And ft minus 1 is the basically information set available at t minus 1. So basically here we are concerned with this, how we'll model this particular variance covariance matrix. So that modeling approach is like this here. St is equal to C plus summation of ai epsilon t minus I transpose ai transpose I from 1 to p. Similarly here summation of bj ht minus j b transpose j from j is equal to 1 to q. So in fact this is the arch term and this is the GARCH term. So here we have to see is the positive semi-definite matrix constant component to making sure that the variance is positive. Then ai is the matrix capturing the arch effects, that is the impact of the past residuals, and bj is the matrices capturing the GARCH effects, that is impact of the past covariances. So this is the general structure we have. To understand better, let us take example of the two variable cases. So here we have the, let's assume yt is the vector of the two variables only, y12, y2t. So the representing the returns of the two financial assets. So the conditional mean in that case it will be mu t is equal to mu1t and mu2t. And the conditional variance covariance matrix will be this h11t, h12t, h12t, h22t. However, because it is the covariance, it will be symmetric. So here we are assuming both will be similar. So here h1t is the conditional variance of y1t, h22t is the conditional variance of y2t, h12 is the basically conditional covariance between y1 and y2t. Now let us first discuss the VECH model. So till now we have discussed the general structure of the multivariate GARCH model. Now how we deal with the variance and covariance matrix, there are the three ways as we have discussed earlier. One is the VECH model. Here the VECH refers the vectorized error conditional heteroscedasticity model. Why we call vectorized, in a minute we will be able to understand. So in case of VECH model, we model the lower triangular elements of the conditional variance and covariance matrix. So basically what happens here, the VECH operator stacks the lower triangular elements of a symmetric matrix into a vector. So that's why we call the vectorized here. So here allows for the modeling dynamics of the variances, covariances in the for which we have the formulation of this structure here. So here St is the conditional variance covariance matrix, C is the vector of constants, Ai and Bj is the coefficients matrices of the arch and GARCH effect. So let us take the two variable case again and let us see what we mean by the vectorized. So basically let us say, so this will have the variance and covariance matrix here. In that we are vectorizing the lower triangular. So basically this is the diagonal element. So lower triangulars, basically we are concerned with this part. So this is the lower triangular. So we use this lower triangular and convert it into a into the vector. Then the dynamics of this we could represent here like this, where the components will be C11 and the arch effect will be A into VECH multiplies this particular multiplication of the past error term. So we will get E square epsilon 1 square t minus 1, epsilon 2 square minus t minus 1 and epsilon t minus 1 into epsilon t minus 2, which is basically capturing the covariance here. Similarly, we will have the GARCH effect in this particular form. Now, if you wanted to expand it form here, so the dynamic equations of these two equations will have this H1 dt, that will be C11 A11 epsilon 1 t minus 1 square. Similarly, A12 epsilon t 2 t minus 1 square, and similarly A13 and the cross multiplication of these two error terms. Then we have the lag of the variance of the first variable, lag of the variance of the second variable, and lag of the covariance. And similarly we'll have for the variance of the conditional variance of the second variable and the conditional covariance of this first and second variable. So these will have the dynamic equation in case of the two variable, and these are the basically we are going to estimate this number of parameters we have to estimate. So if you see what are the advantages we have, we are able to model both variances as well as the covariances, and that is also time varying, that is dynamic in nature. The second, it is the flexible for capturing the cross asset interactions, also the cross market interactions. However, there are the certain limitations we have of this model, or the disadvantages we have the models. First, it requires estimation of the large number of parameters. Basically, the number of parameters, it will be here. For example, in case of two variable, we have to estimate the 21 parameters. And in case of three variable, the total number of parameters jumps to 78. So there is the exponential jump is happening in the number of parameters. Second, it does not guarantee the positive definiteness of the variance and covariance matrix. So sometimes it may be the variance will get the negative, which is not the true. Therefore, we have the second approach, that is the diagonal VECH. In the diagonal VECH, basically what we are doing, it is nothing but the restricted version of the VECH model. So where we are assuming that the cross correlation terms are not significant, we are assuming those are the zero. That is, no cross dependence between the variables in arch and GARCH terms. That's what we have assumed here. So this simplifies the computation and modeling the time varying and covariances. So how that happens? Let's see the general form of the diagonal VECH model. The general form will be like this, where this ST is the conditional variance covariance matrix, epsilon T is the vector of innovation, that is the error terms, AJ, AI and BJ are the parameter matrices respectively for the arch term and the GARCH term, and this is the Hadamard element product, that is element wise product of the matrices. VEC is the operator that vectorizes the lower triangular position of the matrix, and we follow this particular structure for the diagonal VEC. To understand better, let's take the let's limit us to the lag 1, 1. So where we are assuming that both arch term and the GARCH term is 1. Then it simplifies the model like this. Here, what are the advantages? We have the captures the dynamics of variance and covariance through the past errors and the past conditional variances, and it is widely used in the multivariate volatility modeling because of its simplicity in the estimation as well as in the structure, and able to capture most of the dynamics of the financial data. So let us, to have the better understanding, let's take the again case of the two variables where we will have this epsilon T error. So the variance covariance matrix is like this. Then the dynamic equations will be for the variance of y1, it will be only this equation, and for the conditional variance of y2t will be this, and the conditional covariance between y1 y2 will be represented by this. So these are the basically uh, conditional variances and covariances, and we are assuming here it is at the time varying in nature, that is the dynamic in nature. Then what are the advantages here we have? One of the advantages is that it reduces the number of parameters compared to the full VECH model, and therefore it is easier to estimate as well as the interpret. However, the limitations what we have assumes no cross dependence between variables in arch and GARCH terms. Again, it also does not guarantee us positive semi-definiteness of the variance and covariance matrix. Let's see the comparison of these two, that it will be clear what is the difference between VECH and the diagonal VECH, and why we are often use the diagonal VECH rather than the VECH model. So what we can observe here, that the VECH vectorizes the lower triangular including the diagonal matrix, captures both diagonal variance and off diagonal covariances, and the number of parameters for a matrix will be k into k plus 1 upon 2. For example, when we have the two variable cases, what we have the A matrix, that is 2 plus 1 upon 2, that is 3. So we have the two matrix, so that will be A matrix and the B matrix, so 3 into 2, that is 6. So here the number of parameters follows this structure, that it will for a k by k matrix. Now let us see here what we have. Let us say if you have the 3 variable, then we have all the parameters we have to estimate for the matrix here. However, we have to take the diagonal of this. In case of diagonal VECH operator, what happens? We are only concerned with the diagonal elements, not the off diagonal elements. So in that case, number of parameters will be only for a k by k matrix. For here, for the 3 by 3 matrix, we are concerned only of this 3 parameters rather than. So it is hugely reduces the number of parameters. Therefore, it is easier to estimate and interpret. Then there is the third approach of the multivariate GARCH model, that is the VECH model. So in case of VECH model, what we have, the conditional variance covariance matrix is given by this particular structure, where ST is the conditional variance co-matrix at time t, C is the constant matrix ensuring the positive semi-definiteness, A is the matrix capturing the effects of the lag shocks solenoid T, and B here. So basically it ensures the positive semi-definiteness, and it is parsimonious in the parameterization compared to the unrestricted model. So let us take the two variable example, and that will be easier to understand what we have different in the VECH model. So in that case, what we have, we have the variance and covariance matrix, and the variance dynamics will be captured by this. So here the C is the lower triangular matrix, A is the 2 by 2 matrix for the shocks, and B is the 2 by 2 matrix for the lagged variances we have. So what are the advantages we have in the VECH model? Ensure the positive semi-definiteness of ST, and the captures the cross variable effects and the spillovers. High computational cost for we have estimation. Parameter interactions are complex to interpret. So today we have discussed about the multivariate GARCH model, and we have discussed the three approaches of that is the VECH model and the diagonal VECH model and the VECH model. In the next class, we'll extend this, where we'll talking about the correlation matrices. Okay, rather than modeling the variance and covariance, if we are able to capture the correlation, how we'll model that approach. So thank you so much. See you in the next class.